In this video, we continue with our discussion of shapes of molecules from Chapter 10. In this video, we're going to cover VSEPR, valence shell electron pair repulsion theory, which is a way to rationalize three-dimensional structures of molecules. We'll be able to take Lewis dot structures, make predictions about shapes, and then we can see how those shapes compare with experimental evidence. The concept behind valence shell electron pair repulsion theory is that around a central atom, for example, sulfur and sulfuric acid, each group of valence electrons around the central atom locates itself as far as possible from the other electron groups. They want to minimize repulsions. Therefore, the electron groups repel one another and develop a geometry that minimizes those repulsions. Now, any group of electrons is electrons that occupy a localized region around an atom. So we would see that one group of electrons would be either a single bond, or a double bond, or a triple bond, or a lone pair, or a free radical electron, like in nitrogen dioxide. Each of those would be an electron group: single, double, triple bond, lone pair, or free radical. And so these are the 5 predominant shapes that we'll look at, and these cover the large majority of main group molecules that we would consider, and it also covers all the organic systems for which you'd have any concern, organic or biological molecules or biochemical systems. So we'll have, hopefully you remember this from your high school geometry, so you're comfortable with these sorts of shapes. If we have 2 groups, we'll see that that'll produce a linear structure. So 2 groups that repel one another, if they want to get as far apart as possible, they go to opposite sides. So that produces a linear structure. If we have 3 groups, they will optimize their structure or shape by going to a flat structure where the 3 groups go on to a triangular structure in a plane. That's what we'll call trigonal planar. If there are 4 groups, they minimize by not going into a square, but going into a tetrahedral structure. 4 groups gives us a tetrahedron. 5 groups produce a trigonal bipyramidal structure. That is a trigonal plane with 1 group above and 1 group below. So we'll have 2 different bond angles there, we'll see. And finally, 6 groups form an octahedral structure. It's important to remember the difference between electron group arrangement and molecular shape. The electron groups will determine how the nuclei move. So electron group arrangement is defined by both bonding and non-bonding electron groups. But the molecular shape is identified by the relative positions of the nuclei. And we'll look at a number of examples of this when we go on to our mechanics videos for this chapter. So to reiterate, the molecular shape is the 3-dimensional arrangement of nuclei joined by the bonding groups. This is defined only by the relative positions of the nuclei. While the electron groups will determine where the nuclei go, the electron groups are not part of the final shape analysis, but only the positions of the nuclei. The molecular shape is classified using this designation below. If you find this comfortable to use, that's great. If there's a alternative means where you can take the geometries that we develop and just recognize them, that was fine too. So we have A is our central atom. X would be the atoms surrounding that central atom. And M would be the number of surrounding atoms we have. And then E, of course, is our lone pair electron group. And then N would be the number of lone pair electrons we have. So we'll see that we can classify the molecular shape using these. But the molecular shape is really only defined by the central and the surrounding atoms. The lone pairs will dictate where they move, but then we'll identify the shape based on A and X. A bond angle is the angle formed by the nuclei of two surrounding atoms along with the central atom. So in this central picture, we have the central atom A with three X atoms surrounding the central atom A. And so from X to A to X, that angle is what we will call a bond angle. Earlier, we looked at the distance from A to X. We call that the bond length. Bond lengths and bond angles, of course, are crucial in dictating molecular structure. VSEPR has nothing to say about the lengths of bonds. We can approximate those by thinking about whether it's a single bond or a double bond or a triple bond, but VSEPR only tells us about bond angles. That's what we're focused on in this video. The angles shown in figure 10.2, as we'll see, are ideal bond angles, and they're determined just by the basic geometry class alone. The real bond angles deviate from the ideal ones, as we'd expect in many cases. And here are four quick examples where we can have different sorts of bond angles. In the first case, if a central atom A falls into the trigonal planar group and has three identical atoms around it, we will find that when you measure the bond angles by X-ray diffraction or other techniques, the bond angles are 120 degrees, which is the ideal value. But if one of the atoms around that central atom is not an X, for example, it's a Y, if that Y is a double bonded system, we'll see that it's not 120 degrees. While a double bond is an electron group, it tends to be a little bit stouter electron group, and it takes up a little bit more space. Now, if all three of them, like in the third case, are all single bonds, but two of them are identical atoms, and then one is a different atom, like A with two X's and then a Z, again, we won't see a 120 degree bond angle. It'll be close, but in many cases, but it won't be the same. And finally, if we have a lone pair, like in the final example on the right, AX2, we'll find out that the lone pair will be much stouter and takes up much more space. And so the bond angle is not 120 degrees. It gets squeezed down. So the XAX angle is less than 120 degrees. Let's look at this by group. So we'll start off with the linear group. So in this case, if we have AX2, and there are only two electron groups around the central A atom, the molecule will be linear. And examples of this include carbon disulfide, hydrogen cyanide, beryllium difluoride, and many others. And in this case, we see that the bond angle is indeed 180 degrees. If we have three electron groups around the central atom, there are two possible molecular shapes. First, if all three of the electron groups are bonding pairs, so either single, doubles, or triples, then we have a trigonal planar molecular structure, like, for example, sulfur trioxide, boron trifluoride. The nitrate polyatomic ion is a trigonal planar structure, as is the carbonate polyatomic ion. If one of the groups is a lone pair and not an atom, then we have what we call a bent molecule or a V-shaped molecule. Examples of this would be sulfur dioxide, ozone, which we looked at under Lewis structures, lead-2 chloride, tin-2 bromide, and many others. As we said before, non-bonding or lone pair electrons tend to repel more strongly. Thus, a lone pair repels bonding pairs more strongly than bonding pairs repel each other. The lone pair is pulled in closer to the atom. It tends to be rounder and stouter, and this results in a decrease in the bond angle between the bonding pairs. So, for example, in tin 2 chloride, the chlorine-tin chlorine distance is 95 degrees, substantially less than 120 predicted for a simple trigonal planar structure. Double bonds, like we said before, also take up more space. Here's a case of a molecule called formaldehyde, a carbon doubly bonded to an oxygen with 2 hydrogen atoms each bonded to the carbon. In this case, rather than all 3 bonds being 120 degrees, the oxygen-carbon-hydrogen bond angle is 122 degrees, while the hydrogen-carbon-hydrogen bond angle is 116 degrees. A double bond has greater electron density than a single bond and repels the single bond electrons more than they repel each other. Now we'll look at the tetrahedral or 4 electron group arrangement around the central atom. When we have 4 electron groups, they repel one another into a tetrahedral structure. And the tetrahedral structure here for AX4, if we have all 4 of the electron groups involving single, double, or triple bonds, then we have the tetrahedral molecular group as well. So the tetrahedral electron group can give rise to a tetrahedral molecule, and that occurs when all 4 of the electron groups involve a chemical bond. Examples of this are methane, CH4, that's an alkane that we looked at much earlier in the semester, silicon tetrafluoride, and the polyatomic ions sulfate and perchlorate. If one of the electron groups is a lone pair, then the structure is, as is shown in the lower left-hand corner, a trigonal pyramidal structure. Examples of this are NH3 or ammonia, PF3, it's phosphorus trifluoride, and the polyatomic ions chlorate and hydronium ion. If we have 2 electron groups that are lone pairs for a tetrahedral electron group arrangement structure, then we end up with a bent or V-shaped system. And examples of this are water, oxygen difluoride, and sulfur dichloride. Lewis structures really don't tell us as much as the VSEPR structures. They're pictures drawn in flatland. We draw them on a 2-dimensional structure. VSEPR structures, if we're really going to make these, are going to have to be drawn in perspective. And they're best handled by using molecular model kits. When you get to your general chemistry lab course, you will have a lab that will cover VSEPR predictions and use molecular model kits. This will help you to see how this works. When you get to organic chemistry, it's very important to get a nice molecular model kit so you can visualize what structures look like. Now, some folks can visualize 2-dimensional drawings in 3 dimensions well. Others are not, but whether you fit into the easy visualization or not, it's always nice to have a molecular model kit to help you build out what the structure actually looks like. So here's the molecule. This is difluorodichloromethane. That is methane, the carbon atom, 1 carbon atom with 2 fluorines and 2 chlorines around it. You don't need to know this name. You will when you get to organic chemistry, but this is just so you know what this is. And the way this is drawn, in the very center of this picture, you can see that difluorodichloromethane can be drawn two different ways. They really mean the same thing. And it turns out, regardless of how we draw this structure, there is only one version of difluorodichloromethane. And you can see in the panel on the left and right are three-dimensional pictures of a molecular model kit showing this molecule in two different ways. It's the exact same orientation of atoms. Now let's look at the 5-electron group arrangement. This is the trigonal bipyramidal electron group arrangement, and that gives rise to 4 different molecular structures. It's important to note here, for the trigonal bipyramidal system, there are 2 different bond angles, and there are 2 different types of electron groups. So as shown in the upper left-hand corner, the basic trigonal bipyramidal electron group arrangement has a top and a bottom group, and these are what we call the axial groups. They're on the axis of the system. So they're on the up and down axis, like the axis about which the Earth rotates. And then there are 3 groups which are in a plane perpendicular to the axis. These are called the equatorial groups. The 2 axial groups are at 90 degrees. The 3 equatorial groups are at 120 degrees from one another. Now, if we have all bonding pairs and all 5 of the groups involve atoms, then we end up with a trigonal bipyramidal molecular structure like phosphorus pentafluoride, arsenic pentafluoride, or sulfur monoxygen tetrafluoride. That's a trigonal bipyramidal structure. Now, if we have one lone pair, the question you might ask is, where does the lone pair group go? Does it go to the axial or the equatorial? Well, it turns out the axial group has 3 90-degree interactions. And 90 degrees is a very short distance, and so a very tight angle. And so the lone pairs, which take up more space, don't go to the axial direction, they go to the equatorial plane. Because there's only 2 90-degree interactions. And then it has 2 much weaker 120-degree interactions. So this creates what we call a seesaw molecule. And that's shown in the upper right-hand corner. We see examples of this: sulfur tetrafluoride, xenon dioxygen difluoride, the iodine tetrafluoride polyatomic ion, and the iodine dioxygen difluoride polyatomic ion. And it's called a seesaw. As you can see, if you take those 4 atoms, the 2 equatorial atoms could, if they're touching on the ground, the axial atoms become the 2 seats on the seesaw. And so the lone pair takes up a lot of space, but it doesn't define the nuclear structure. It doesn't define the shape of the molecule. The nuclear structure does that. And so the AX4 for the 4 surrounding nuclei define the seesaw shape. If we have a second lone pair, that again goes to the equatorial plane, and we end up with a T-shaped molecule. Examples of this are chlorine trifluoride and bromine trifluoride. If we have all 3 of our groups are lone pairs, then we end up with a linear structure. And xenon difluoride, the triiodide ion or iodine difluoride anion all have linear structures. So for the aqueous, the axial and equatorial positions, 5 electron groups have 2 groups that are different. That's the top and bottom group, and they are at 90 degrees from all the equatorial positions. The equatorial positions are 90 degrees relative to the axial, about 120 relative to one another. Where possible, the lone pairs in the 5 electron group systems occupy equatorial positions. For the 6-electron group arrangement, we end up with an octahedron or an octahedral electron group arrangement. There are 3 molecular shapes that we will look at for this type of system. First, if all 6 of the groups around the central atom involve bonds and are atoms, then we have an octahedral molecule. Examples of this are shown here: SF6, sulfur hexafluoride, which is a very important molecule for technological applications for use in producing plasma displays, and iodine oxygen pentafluoride, which also has the octahedral arrangement. If one of the electron groups is a lone pair, it can go to any of the 6 positions because they're all at 90 degrees. They're all identical. So we pick one and we put it on the bottom here, and then we see that the remaining structure is what we call a square pyramid. It's square pyramidal. And here are the examples like bromine pentafluoride. Finally, if there are 2 electron lone pair groups, they go onto opposite sides of the molecule. They take, like we would think, axial positions, and then the remaining 4 atoms go into a square planar structure. There are a number of square planar structures which are important. One of them is the anti-cancer drug cisplatin, which is a square planar structure as well. In this figure, we can see the various molecular shapes that are available around the central atoms for the elements in period 2 and then in elements in periods 3 through 6. In the elements in period 2, we only have a limited number of shapes because we can only form 4 bonds as a maximum. So we can either have a linear electron group arrangement, trigonal planar, or tetrahedral electron group arrangement, which gives rise to the structures shown in the figure. For periods 3 through 6, we can form more than 4 bonds, and this is when the trigonal bipyramidal structure and the octahedral structures or octahedral electron group arrangements become important. Now, in the next 2 slides, we'll see a summary of the common molecular shapes with 2 to 6 electron groups. And both of these slides are good figures that you should print out and have available to you when you're working via CPR problems. The 2 electron group arrangement, we always have a linear molecular structure. For 3 electron groups, we have a trigonal planar electron group arrangement, which can give rise to the trigonal planar molecular structure or a V-shaped or bent molecular structure. With 4 electron groups, we have the tetrahedral electron group arrangement, which can give rise to the tetrahedral molecular structure, the trigonal bipyramidal or the trigonal pyramidal structure, or the V-shaped or bent structure. Now note that the V-shaped or bent structure for the tetrahedral electron group arrangement is less than 109.5, whereas for the trigonal planar electron group arrangement, the V-shaped or bent structure is less than 120 degrees. So there's a significant difference there. Next, we have 5 electron group arrangement, giving rise to the trigonal bipyramidal electron group system. This can give rise to a trigonal bipyramidal molecular structure. 1 lone pair gives us a seesaw structure. 2 lone pairs gives us a T-shaped structure. 3 lone pairs gives us a linear structure. Finally, the 6 electron group arrangement gives the 6 groups forming an octahedral electron group arrangement, which can give rise to an octahedral molecular structure, a square pyramidal structure, or a square planar structure. So in order to get to a VSEPR structure, we need to start with our molecular formula, from which we know how to produce a Lewis structure, which we covered in the previous video. Based on the Lewis structure, then we count all the electron groups around the atom of which we're considering or looking at, and that will give rise to the electron group arrangement. Electron group arrangement will identify the bond angles, which will ultimately define the molecular shape. There are no bond angles for lone pairs, though lone pairs can be identified as arising at a particular location around the central atom. Some molecules, in fact, many molecules, will have multiple shape centers. Two examples are shown here. On the left is the molecule ethane, C2H6. That was one of the alkanes that we saw earlier in our naming of alkanes. And C2H6 has the Lewis dot structure where two carbon atoms have a single bond, and each carbon atom has 3 hydrogens singly bonded to it. Therefore, around each carbon we will have a molecular structure, and around each one we have a tetrahedral electron group arrangement. And since all the atoms are involved in bonds, then we have a tetrahedral molecular structure around each carbon atom. Next we have the ethanol molecule. We looked at this a little bit earlier when we were looking at isomeric structures. Ethanol is shown here, CH3CH2OH, sometimes written as C2H5OH. This is the alcohol that is in consumable products, liquors, and various other alcoholic beverages. Ethanol is poisonous, but it is minimally poisonous, and so your body can tolerate lower amounts of it and can detoxify it unless you have too much, in which case you can die. So we have 2 central atoms, the 2 carbon atoms. One of the carbon atoms has 3 hydrogens and then 1 carbon bonded to it. That's a tetrahedral electron group arrangement. Then we have another carbon atom, which has 2 hydrogens, a carbon and an oxygen, and that's a tetrahedral electron group arrangement. Now finally, there is a third central atom in this system, and that is the oxygen atom. And the oxygen atom has 2 lone pairs and 2 bonding pairs nearby, and this forms a bent structure. And we will see that this is very important in determining many of the properties of ethanol. Finally, we'll see that we can use these molecular structures that we've generated from VSEPR to predict some important properties of molecules. We start off with the simple idea of electronegativity difference, that's the delta En. The electronegativity difference for 2 pairs of atoms that are bonded together give us an idea of the dipole on that bond. That tells us something about the bond polarity. We looked at bond polarity earlier when we were in Chapter 9 looking at covalent bonds. Now, if there are multiple bonds within the system, we have to add up all those dipoles, and we generally, you can do this computationally, but you can also do it simplistically, and we'll look at simple systems where we can add them just in your mind, and we can come up with an overall molecular polarity. The overall molecular polarity tells us something very important about what we're going to find out are called intramolecular forces. And intermolecular forces dictate the physical properties, the solubilities, and the chemical reactivities of molecular systems.